Physical laws are formulated using the infinite continuum. Equations describing fluid dynamics or orbital mechanics assume infinite precision, but computational hardware is strictly finite. To bridge the gap between infinite mathematics and finite processors, the industry relies on a compromise called floating point arithmetic. Floating point systems represent continuous numbers by constantly truncating data. They force microscopic approximations at the hardware level during every single calculation, deciding exactly where to slice off decimal points to fit available memory. These approximations compound. When running millions of iterations through a PDE solver, micro-rounding errors accumulate exponentially. A PDE, or partial differential equation, is a mathematical tool used to describe how quantities change relative to multiple variables, such as time and space. Because of this continuous drift, driving analytic error tolerances, represented by the variable epsilon, closer to zero requires massive, nonlinear increases in processing power. Epsilon is a symbol used in analysis denoting an arbitrarily small positive quantity, representing the maximum allowable difference between an approximation and the true value. Traditional continuous modeling places numerical analysis in a paradox. Relying on floating point approximations to achieve higher physical accuracy results in computational instability. The Deterministic Operator Calculus, or DOC, is a mathematically rigorous exit from the floating point trap. It abandons approximation entirely in favor of algebraic certainty. DOC achieves this by replacing continuous real number approximations with a strictly finite algebraic substrate. A finite algebraic substrate is a computational environment where all possible values and operations are restricted to a fixed, finite set of integers, preventing any numerical drift. Within this finite framework, interior computations are executed exactly. By locking operations to whole integers, the system encounters absolutely zero rounding error. These exact finite states must eventually map back to classical, continuous Banach spaces. A Banach space is a complete vector space equipped with a norm, providing the rigorous environment needed to measure the size of continuous mathematical functions. We will construct the three exact mathematical layers of the DSC architecture to prove how finite integers can definitively map the continuum. Mastering this three-layer architecture allows for the construction of parameter-free, deterministic physics models. The bedrock of Layer 1 is the finite commutative ring R equals Z sub D, derived from an integer base B, where the modulus D equals B minus 1. The base B digital root map governs the dynamics of integer powering sequences on this substrate. Axiom A3 dictates the mathematical segregation of the ring into two categories, multiplicative units and non-units. The units cycle with fixed bounded lengths governed by Euler's totient function. Euler's totient function counts the positive integers up to a given integer that are relatively prime to it, which defines the maximum possible cycle size on the ring. The non-units behave differently. Their powering sequences inevitably collapse into stable fixed-point attactors. They reach a single value and halt. This topological sorting ensures algorithmic finiteness. Every integer sequence falls into a predictable loop or a fixed point without ever requiring infinite precision. This predictable, finite behavior provides a stable mathematical foundation. Because the rules of the ring are locked, calculation drift is physically impossible. Layer 2 outlines how we manipulate data on the substrate using linear DOC operators, mapping L2 of IN to L2 of IN. An L2 space is a mathematical sequence space where the sum of the squares of the values is finite, acting as the standard environment for these discrete operators. The canonical DOC smoothing operator is the discrete triangular Fejér type kernel. This kernel possesses mandatory properties. It must be symmetric, maintain unit mass, and remain positive semi-definite. A positive semi-definite matrix never yields a negative value when applied to its inner product. These properties are enforced by the DOC legality axioms, a set of strict contracts governing what constitutes a valid operator in this architecture. The calculus explicitly bans illegal operators. Highly oscillatory, sign-changing windows designed to force artificial, fragile mathematical cancellations are forbidden.
Axiom 04 introduces a critical mechanism, the sharp +1 floor. This floor represents the irreducible unit of discrete boundary error. When you compare smoothed continuous weights to sharp integer-valued discrete counting, there is a discrepancy of exactly 1 unit at the boundary. These legality contracts strip away arbitrary parameter tuning. They ensure that all finite operations on the substrate remain mathematically bounded and objective. We now have an exact discrete mechanism. The challenge is proving that these finite matrices correspond rigorously to continuous physical reality. This is the function of layer 3, the universal finite to exact transfer, and its specific doc implementation, CDUT. UFET and CDUT are transfer theorems providing a mathematical bridge for lifting finite discrete states back to the continuous world. The bridge to the continuous is the DOC residual schedule, eta of h. The first term limits discretization error, controlled strictly by the physical mesh scale. The second term bounds smoothing window error based on the ratio of Fejér span over grid size. This schedule governs the mechanism of gamma convergence. Gamma convergence is a mathematical concept in the calculus of variations that guarantees the minimum values of approximate functions converge to the minimum of an exact continuous function. Under gamma convergence, discrete minimizers are mathematically forced to converge to continuous minimizers precisely within this exact eta envelope. UFET and CDUT ensure that perfectly exact discrete math on the hardware yields rigorously bounded continuous physical results in the real world. We apply this 3-layer DOC engine to actual differential equations through the substrate PDE framework. SPDE is a methodological framework built on DOC that represents classical partial differential equations as exact finite operator systems. When a classical PDE is mapped into SPDE, all interior computation relies entirely on the finite ring arithmetic established back in layer 1. This chart shows classical solver operations mapped against the analytic error tolerance epsilon. As the tolerance shrinks towards 0, classical costs rise exponentially. In contrast, SPDE computational scaling remains completely flat. Theorem 6.2 states this explicitly. The computational cost per degree of freedom per update in SPDE is entirely independent of the continuous analytic error tolerance epsilon. This epsilon independence allows for immense precision mapping without exhausting hardware limits, because the system never iterates to hunt for a floating point decimal. SPDE decouples mathematical accuracy from computational cost, allowing for simulation depths that remain stable even as error tolerances shrink. The foundational validity of the entire DOC framework rests on the conservativity meta-theorem. DOC introduces 0 new axioms into mathematics. It is fully compliant with standard Zermelo-Frankel set theory. ZFC stands for Zermelo-Frankel set theory with the axiom of choice, the universally accepted foundation of modern mathematics. Because DOC is a definitional extension, every conclusion it reaches is already a verifiable theorem of standard mathematics. There are no hidden physical assumptions. The application of this conservative framework leads to the Marithmetics derivation engine, which strictly enforces DOC admissibility contracts. This engine derives continuous standard model physics entirely from parameter-free integer processing. The standard model is the physical theory classifying all known elementary particles and describing 3 of the 4 known fundamental forces. The flagship achievement of this engine is extracting the fine structure constant, represented as 137, and particle mass ratios, like 107 and 103, strictly from base gauge invariant integer triples. These predictions emerge as dimensionless ratios. They require 0 human scale choices, 0 physical units, and 0 tunable parameters. Doc and Marithmetics prove that the continuum of the universe is not an approximation. It is a reality that can be derived flawlessly through the uncompromising laws of finite arithmetic.